Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. This is the second part of DC analysis of the FET. So the first, in the second part, we will continue the circuit configuration for DC analysis of the FET. The first one is voltage divider, as you can see in the figure 7.21 here. This is a little bit, if you remember the self-bias, if the self-bias only, we didn't include R1 here, only R2 and RS here. And then in here, we insert the R1. So because of this is the voltage divider, R1 and R2, so we call this configuration as the voltage divider configuration. And then in this figure 7.21, we found that this is the coupling capacitor here, C1 and C2 here. And also, this is bypass capacitor. Okay, so bypass capacitor is, yeah, I will explain in the AC analysis why we need bypass capacitor here. Okay, so since the IG or gate current is equal to 0, so the Kirchhoff current law requires that the IR1 is equal to IR2. So we can draw for this one that the VG is equal to R2. This is the voltage divider, VG here, the gate voltage here, this is the VG here, is equal to R2 multiplied by VDD per R1 plus R2. So this is the VG here using the voltage divider, R1 and R2. We can calculate like this one. So we see that this is the VG. And then we can apply the, so the VG is from this node to the ground here. This is the VG here, okay, or VG here. So we can apply the Kirchhoff law in this loop here. So minus VG minus VGS minus VRS is equal to 0. So VGS is equal to VG minus VRS. Or we can substitute the VRS here like the self-bias. IS dot RS, so IS is equal to ID, so we can calculate that VRS is ID RS. So if we apply to this equation, so VGS is equal to VG minus ID RS. And then we can using the mathematical and then the graphical. This is the blue line here. This is the device characteristic. And then how to draw the circuit characteristic, we need to draw the black curve like this one. So the first one, from this equation, the VGS is VG minus IDRS. We plot that ID is equal to 0. ID is equal to 0 here. So the VGS is equal to VG because of this is equal to 0. So the VGS is equal to VG. So this is this plot here. And then the second, when the VGS equal to 0, so the ID here, in this point, is VG per RS. And then VG we can get from this equation, and RS is the constant, so we can find from the circuits. So we can make a calculation, this point, and then we draw from this point to this point. And the intersection between the black line and blue line is the key point here. So we got that the key point or ID key. So this one is ID key, and here is VGS key. Okay, here. Okay, and then another parameter, we can calculate the VDS equal to VDD minus ID RD plus RS, and then VD is, so the VD is VDD minus ID RD. Okay, and then VS is IDRS, and then IR1 and IR2 is VDD per R1 plus R2, and then VGS is VG minus IDRS. Okay, so we can change the key point by changing the RS like this one. If the RS is larger than RS2 here, so the key point will 0 like this one from this point, move to this point. So this is the key point changing if we increase the value of RS. Okay, so this is the example. Determine the following for the network of figure 7.25. Okay, so we can see that from here. The first one, the procedure is we have to plot the device characteristic like the blue line. So we can, using the Shockley, IDSS per 4, IDSS is 8 milliampere, so we got that ID is 2 milliampere, and VGS is VP per 2 is minus 2 volt. So this is the IDSS, 8 volt, and then this is the VP minus 4, and then we put another, like when the IDSS is equal, IDSS per 4, so the VGS is VP per 2 as minus 2, so we can draw this one. So this one, this point for device characteristic here and then here, so we can get the third point. So we can draw the blue line here like this one. This from this point to this point and this point. And then from the network equation, the first one we have to define the VG. VG here is R2 VDD per R1 plus R2. So R2 is 270 kilo ohm and R1 is 2.1 mega ohm. So we got that VG is 1.82. And VGS is VG minus IDRS. So we got that this equation 1.82 volt VG minus ID multiplied by 1 per 5 kilo ohm. So when ID is equal to 0, VGS is equal to plus 1.8. So we got that here when ID is equal to 0. And then when VGS is equal to 0, this one, so we got that ID is 1.82 volt per 1.5 kilo ohm. We got that this is 1.21 milliampere. And then we plot this graphic here from this point. We got that intersection between the device characteristic and circuit characteristic. We got this point and we grow from it. This is the ID key and then the VGS key. ID key is 2.4 milliampere and VGS key is 1.8 volt. Okay, so VD is the second question. Is VD is VDD minus IDRD. So we got that VDD is 16 volt, ID is 2.4, and RD from this is 2.4 kilo ohm. So we got that VD is 10.24 volt. And Vs is IDRS, ID is 2.4, and then RS is 1.5 kilo ohm. So we got that Vs as 3.6 volt. And then VDS is VDD minus ID multiplied by RD plus RS. We using this constant, we got that VDS is 6.64. Our VDS is simply by VD minus Vs. VD is 10.24 from here, and then Vs is 3.6. We got that 6.64 volt. Okay, and seldom requested that VDG we can determine when VDG is VD minus VG. VD is 10.24 and VG is 1.82 volt. We got that VDG is 8.42 volt. Okay, so this is another network 7.27. So you can using similar procedure with previous that I explained, and you can solve this equation. And then this is for N-channel depletion type MOSFET in figure 7.30. Determine that I hope you remember what is the differences between depletion type and enhancement type. For depletion type, the channel under the VG here, this is the source, this is the drain, and this is the gate. This is the silicon oxide here, and then here is channel here, the end channel. So from the depletion type, the channel is exists from the beginning. I mean that we construct the channel under the silicon oxide. So this is the depletion type, and then in the notation, the here is solid here, and the enhancement type is the dashed line in notation. Okay, so determine the ID key and VGS key and also VDS from the circuit. And then first we have to plot the device characteristic or blue line. Yeah, using the the IDSS. Sorry, the IDSS is 6 milliampere and VP is -3. So we got 2 point, -3 for VP and IDSS 6 here. And then another key point, another device character, the point for device characteristic, we can use the IDSS per 4 is VP per 2. So IDSS per 4 is 1.5 here, so this point, and then this is minus 1.5. So we can draw a line between 3 device here, 3 characteristic. And then another is we have to plot the circuit characteristic or black line, okay, or here if you want to put another point in device characteristic, yeah, simply for simple you can using the Shockley here, and then yeah you can find the equation. IDSS is constant, VP is constant, just put the VGS like this one. From this is for example this VGS1. So VGS1, put this equation, so you got that ID is 10.67. So here 10.67. So this is another point. So just make yeah like this one. So this is the device characteristic of the FET. Okay, then yeah, we have to calculate the VG here. VG is R, like from this equation, so VG. Okay, R2 per VDD per R1 plus R2 here. So, okay, so we got that VG is 1.4 volt. And then we put that equation. VGS is VG minus IDRS. VG is 1.5 volt and ID, and then RS is 750 ohm. So we got from setting ID is equal to 0, VGS is VG is 1.5. So we put this one here. When the ID is 0, VGS is 1.5. And then when VGS is 0, ID is VG bar RS is 2 milliampere here. Okay, so we put, this is the circuit characteristic. The intersection is the key point here. And ID key here is 3.1 milliampere and VGS key is 0 minus 0.8. Okay, then the equation B, VDS is VDD minus ID RD plus RS. So we got that VDD is 18 volt, ID is 3.1 from here. And then RD is 1.8 kilo ohm and RS is 750 ohm. We got that VDS is 10.1 volt. Okay, so this is the answer of the equation. So this is a repeat example when the RS is 150 ohm. So you can follow in this PPT file. Okay, this is also the similar. You can find by yourself. And then for depletion type of MOSFET, for example, determine the VDS for the network. Okay, in figure 7.35. Okay, so in the direct connection, we make a direct connection between the gate to source terminal here. And then so it must be VGS is equal to 0 because we connect the gate to the ground here. So the VGS is equal to 0. Since the VGS is fixed to 0, so the drain current must be IDSS. So the VGS key must be 0 and ID key is equal to IDSS is 10 milliampere. So the VD is VDD minus IDRD. VDD is 20 volt, ID is 10 milliampere, and RD is 1.5 kilo ohm. So we got that VD is 5 volt here. And then this is for N channel. enhancement type MOSFET. So for N channel, we didn't use the Shockley, we used another equation. So the ID is equal to K multiplied by VGS minus V threshold quadrats. So from here, the ID is equal to K multiplied by VGS minus V threshold quadrats. So the ID on is equal to K multiplied by VGS on minus V threshold quadrat. And then K is, the constant here is ID on per VGS on minus V threshold quadrat. Okay, and then this is the device characteristic for enhancement type of the MOSFET. Okay, so okay, I will continue for the enhancement type. Here we can use the feedback biasing arrangement for the enhancement type. So we connect the RG to the output here. So we call it feedback. Okay, since IG is equal to 0 and so the VRG is equal to 0. So the VD here, so because there is no current here, the current is equal to 0 here. So the VD is equal to VG. And then because source is connected to ground and source is connected to ground, so the VD equal to VG is similar to VDS equal to VGS. And for the output of the circuit, here the VDS is equal to VDD minus IDRD and VGS. So because of VDS is equal to VGS, so the VGS is equal to this equation, VDD minus IDRD. So from here we can plot that VGS is equal to VDD when the ID is equal to 0. Okay, so when the ID is equal to 0, so VGS is equal to VDD. And then when VGS is equal to 0 here, so the ID is VDD per RD. So we can draw the black line here for the circuit configuration, and then we got key point here. This is the ID key here, and then this is VGS key. Okay, so for example, determine the ID key and VDS key for enhancement type of MOSFET. We can see that this is the ID on, this characteristic of enhancement. ID on is 6 milliampere, VGS on is 8 volt, VGS threshold is 3 volt. The first one, we have to plot the device characteristic by using the K. K is ID on per VGS on minus V threshold quadrat. So from here we can see that ID on is 6 milliampere, VGS is 8 volt and V threshold is 3 volt. So we got that K is 0.24 multiplied by 10 power of minus 3 ampere per volt quadrat. And then so we can check some point here. It's like from VGS is equal to 6 here. So we got that ID is 2.16 here. And then when VGS is 8, and then VGS is 10, so we got 3 point here. So we can draw the device characteristic. And then for network bias, we see that from equation VGS is VDD minus IDRD, like I explained before. So VDD is 12 volt here, and then the ID and RD is 2 kilo ohm here. So we check when the ID is equal to 0, so we got that VGS is equal to VDD is 12 volt. And then when the VGS is equal to 0, so ID is 6 milliampere. And then we got this one 6 milliampere when VGS is 0, and VGS is equal to VDD when the ID is equal to 0. So intersection between, so we can draw the black line, and intersection is key point. Here is ID key 2.75 milliampere and VGS key is 6.4 volt. Okay, so this is the enhancement type. We can use the voltage divider also here for enhancement type, similar to the depletion type, except that in this device characteristic here, I mean that if in depletion type we use the Shockley equations, okay, and in this enhancement type, we use this equation. So the first one, we have to determine the VG here. VG is similar with the depression type R2 VDD per R1 plus R2. And then we can draw from the Kirchhoff law here, plus Vg minus Vgs minus Vrs is equal to 0. So the Vgs is Vg minus Vrs. And then Vrs is IDRs. So this is the Vrs, is ID.rs. So Vgs is Vg minus IDRs. And then for the output section, VRS plus VDS plus VRD minus VDD is equal to 0. So the VDS is VDD minus VRS minus VRD. So we can see that because of VRS is IDRS and VRD is IDRD, so we got that VDS is VDD minus IDRS plus RD. Okay, so from here we can solve similar to depletion like this one, this example. From the device, V threshold is 5 volt, IED on is 3 milliampere, and VGS on is 10 volt. The first one, we have to determine the equation is AD key, VGS key, and VDS. The first one, we determine the VG here using the equation R2 VDD per R1 plus R2. We got that VG is 18 volt, and then the VGS is VG minus IDRS. We simply put that the VG is 8 volt and RS is 0.82 kilo ohm. From here we can get when the ID is equal to 0 and VGS is equal to 0. So we get 2 points here. Here VG is equal to 18 and ID is equal to 21.95. So intersection here is key point. So the ID key is 6.7 milliampere and VGS key is 12.45 volts. Okay, this is the how to define the network analysis. How to define the black curve like this one. And then this is how to determine this one, the blue line. Yeah, very simple. The first one, we have to determine the K, the constant K. K here is ID on per VGS on minus V threshold quadrat, and you can find that ID on, VGS on, and V threshold in here. Okay, and then put in this equation, you got that K here. So how to determine the device point here? By simple using this equation, ID is K multiply VGS minus V threshold quadrat, and then put K, and then VGS is variable, and then V threshold is 5. So you can put some point like in VGS is equal to 5, VGS equal to 10, VGS equal to 15, VGS equal to 20 here. So you can make a variable VGS here, and then you can determine the ID by this equation. And then you can draw the blue line, and the intersection is K point. Okay, just simple like this. That's one. And then from the plot graphic, we get the ID key is 6.7 milliampere and VGS key is 12.5 volt. So the VDS, the next question is VDD minus ID RS plus RD. We got that VDS is 14.4 volt. So this is a summary table for GFET. Okay, fixed bias, soft bias, voltage divider bias GFET, and then GFET common gate, and GFET when VGS key is equal to 0. And then when we connect GFET RG to the ground, RD is equal to 0, and then this depression type for fixed bias, depression type for voltage divider, this is the enhancement type for feedback I explained just before, and then this is enhancement type for voltage divider bias. Okay, so I think this is the end of the second part. And then another rest of the PPT file you can learn by yourself if you want to know more detail about the FET DC analysis. But I think this is enough for you to understand how we can define the key point of the FET. And then after midterm, you will study about the AC analysis, and AC analysis need a DC analysis. Okay, I think this is enough for the part 2 of this chapter 7. Okay, thank you very much for your attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.